Hello, everyone, and welcome to this webinar where we're going to discuss how we can ensure vehicle pass-by noise compliance with acoustic simulation. My name is Thanos Poulos, and I will be your guide and presenter in this presentation in this webinar. So first, let us start about why we care about this type of simulation and why we care about pass-by noise in general. And for this, we have to take a look at why this is an issue. Well, noise has emerged as a leading environment nuisance in the WHO European region, where more than 1 in 4 Europeans, or about 125 million people, are affected by noise levels of more than 55 decibels that come from road traffic. And from these people, more than 20 million experience annoyance because of these noise levels. There is sleep disturbance, which is much more important since sleep can impede productivity. And we also have much more important health impacts, and also it could have death as well that comes from environmental noise. So this is an important problem that we would like to solve overall. And the way that this has been done so far is by introducing regulations, especially in Europe, which is a place which has lots of different stringent regulations. The European Union cares a lot about the environment in most cases. There has been a very strict pass-by noise limit, and we can look at this limit evolution in the following chart, where starting from the 1970s, where the first legislation was passed for pass-by noise, and the limit was set at 82 decibels in the A scale. Then, after 20 years, the noise limit was reduced to 74 decibels, which is a very big decrease in the noise pollution. And after a few years more, it was further reduced in 2016 to 72, in 2020 to 70, and there will be a new regulation coming up in 2024, where this will be further reduced to 68 decibels. So you can see that from the 1970s up to the 2020s, which is about 50 years, we have had a decrease in the noise level regulation from 82 to 68 decibels, which is 14 decibels. And you have to remember that a 6 dB decrease means decreasing the noise level by 15%. So this is really a huge effort that is being placed on reducing pass-by noise. Now, of course, looking at this from the OEM point of view, from the constructor point of view, very often they treat acoustic design in two ways. One of these can be regulations. Do we need to comply with a specific regulation to allow us to put our vehicle in the market? And the second is that right now, very often customers, meaning drivers and passengers, treat vehicles as a product, of course, and need to have very good acoustic performance. So acoustic comfort is treated as a feature. In any case, in this webinar, we'll talk about pass-by noise, which is mostly related with regulation. So let us right now look at pass-by noise regulation compliance. Let's start our journey in this topic to see what the regulations are, how do we measure pass-by noise, and how acoustic simulation can help us uh, comply with pass-by noise by reducing costs and do that even fast. And let's first look at how we measure pass-by noise overall. And this is done based on the procedure that is described in the ISO 362 standard, where a vehicle has to cross a 20-meter measuring zone, which in its middle has, at the distance of 7.5 meters, two microphones, one of each side. As the vehicle goes through the zone, the microphones capture the noise level, and at the end, we can look at this noise level in comparison with the progression through the test zone and see if the noise that our vehicle makes is above or below the maximum allowed level. If it's below, then it is good. That means that we comply with the regulation. But if it is above, then that means that we need to go back to the drawing board. We need to add maybe some absorptive materials. Maybe we need to change a few things so that we can actually comply with the pass-by noise regulations. And the challenges for this is that most of the time, this type of test comes very late in the development process. And this is because you need actually a real vehicle to do this test. So this is really at the end of the process. Also, it's a very expensive test to perform. A few tracks that you will need to go to this type of testing, and it's very hard and costly to make changes late in the development process, which is a very important point. So we need actually to be able to do these types of tests a bit earlier in the process, so we can actually have compliance with the pattern regulation once we are there and doing the test. Besides the full vehicle noise, we can also separate this into different parts which make noise in reality. Not everything in the vehicle makes noise, but there are some parts which contribute more to the overall noise level. And this tends to be, in most cases, the engine, the exhaust, and the tires. There are also other parts, of course, but these tend to be the most predominant sources of noise for pass-by noise. And since we're here dealing with linear acoustics in most cases, so here we have linear acoustics in reality, then we can very easily decompose this problem, the absolute noise level that we need to find, into two specific different problems. One is related to the noise source, meaning tire noise, engine noise, exhaust noise. And the second thing is about how this type of noise propagates to the microphone, meaning what is the acoustic transfer function. So what is the pressure at the certification microphone due to an excitation from the exhaust. If we recombine those together, then we can get the absolute noise level. So this type of approach can help us be a bit more flexible in how we evaluate pass-by noise, especially when it comes to simulation, but also with tests as well. The noise level recorded due to the pass-by noise test is often analyzed by decoupling noise source and acoustic propagation through the computation of acoustic transfer functions, as I mentioned just above. Let us then talk a bit more about vehicle noise sources. And here I put a number of different noise sources, but the most predominant one in terms of exterior noise tend to be the powertrain noise and vibration, tire noise, road vibrations very often, and exhaust noise. This is because very often we can hear that, but in most cases, exhaust noise, tire noise, and powertrain noise will be the most important parts. Loudspeakers are mostly for the interior comfort. Wind noise is again more from the interior point of view. It's not very easy to have exterior noise that is because of the wind. So in this presentation, we will mostly talk about powertrain noise, tire noise, and exhaust noise. Right. So now that we have an idea about how we compute what are our noise sources, then we can go ahead and see how we can simulate these noise sources and also the acoustic transfer functions, or how simulation can help us do pass-by noise evaluation. And at first, we need to ask ourselves, so, okay, why do we need to do simulation? Well, a very obvious answer is that since the test is very expensive, we have to do something else. And simulation can be very good at providing insight much faster. So here I have four types of topics that simulation can be used for pass-by noise. Um, and the first one, I will explain each of those separately in the next few slides. But the first one is that we can go easily from component to the system, meaning we can test individual components, individual parts, as well as the complete system. Simulation can provide us with a way to do easy source recombination, meaning we can have some dedicated utility that allows us to do specific recombination between different noise sources and different acoustic transfer functions. It can provide deeper insight and allow us to test virtual solutions. And also it can provide results faster and most importantly earlier in the process, so we can take some further decisions about how our product will behave in terms of pass-by noise. Let's look first at the component to system level. Well, of course, we know that in simulation, we can very easily do a type of component level simulation, meaning that we just put the component in an isolated environment and we see what is its performance with respect, in this case, to noise. But of course, the performance of a component in an isolated environment is not the same often as when we put it in the actual if we install it in the actual environment. And it's, for example, if we put a tire in its position in the vehicle. So this gives us an idea of having both types, both the component level and the system level, so we can see how the component works both in an isolated point of view and do modifications there if we need to, and also how it performs inside the actual system. And again, we can see how it performs there. We can do some modifications. So overall, the simulation allows us to go both into the component and the system level point of view. About source recombination, which I mentioned before, here I talked about a bit about this specific utility that we can have. And actually, in since 2021, Action features a utility that can be used for source recombination. It's called the Action Workflow Manager. So this workflow manager can take into account various different sources, such as powertrain noise, intake and exhaust noise, as well as tire noise. It can also take into account the microphone position, the test track information, the pass by noise setup. And at the end, we can compute transfer functions around the vehicle. So we have all the necessary ingredients to perform a pass by noise analysis. But then we need to take all of this and put it together. And this is what this workflow manager is able to do. So what it does is it takes some information from both simulation and tests, if you have them available. It can perform recombination to obtain the noise levels, identify problematic noise sources and paths, and perform what-if scenarios to reduce path by noise. And all of this has nothing to do in reality. In this case, with simulation, we just take all our inputs. So those come from simulation. Some of those may not come from simulation, and put them together and can be used by a non-expert person, by a person that does not really know how to use simulation. The third topic was about deeper insight and testing virtual solutions. So the thing about simulation is that it can provide us with a very large amount of inputs. Measurements tend to have only one input, meaning that you just have, one output, uh, meaning that you just have the pressure on the microphone for the test. It does not really tell you what contributes to this pressure. It does not really it doesn't really tell us how this pressure comes from the vehicle up to the microphone. And these are all things that simulation can provide insight on, meaning which components radiate the most, how noise propagates, and of course, give us ideas about how it can be mitigated. After we have an idea about all of that, then we can try to apply solutions and test them virtually. And we can test possible mitigation techniques such as acoustic treatments by adding them into the simulation model and evaluate the performance. So we can very easily test new solutions virtually directly with simulation. This is a very big advantage, of course. We can see very easily if now our vehicle can comply with the regulation or not by just modifying a few things. And finally, of course, the main advantage of simulation is that it can provide results fast and early in the development process. And as I will show you also later, with quite a good accuracy as well. But let's talk a bit more about having fast results. Well, an important thing that we could have is that very often the meshes of the simulation depend a lot on what is the frequency. And if we just use meshes that are only available for higher frequencies, of course, these are valid for lower frequencies as well, then it takes a large amount of time. So having adaptive meshing generation technique where the computational mesh is adapted to the frequency, this can make the computation faster and more efficient overall. Then we have some solver optimization where we have specific settings of the solver that can allow us to reduce calculation time maybe up to 3 times or even more. And of course, uh, by using parallelism, meaning a multiple amount of cores, then we can get solutions much faster, meaning in a very much in an industrial time frame of maybe even 1 day or 2 days, depending on what is our target model and our target frequency. This sounds all good and nice for simulation, but what are some of the challenges as well? Well, simulation is also facing a number of challenges, and some of those come with replicating the measurements, meaning can we do the same thing as the measurements but in a more efficient way? We have to tackle larger models in real life when we do our tests. If you have a truck, a big truck, or a small car or a motorcycle, it doesn't really matter what is the size of the model. You can definitely measure that, but in simulation we have challenges in that space. And also, pass by noise can be quite complex to post-process in simulation. So there we need to have a way of mitigating this type of post-processing and creating a very easy way to do that. Let's look at all of those and maybe what are some solutions to that. For the first topic, which is replicating the measurements, well, let's go back to how we measure pass by noise. And again, we have our 20-meter test track. We have our vehicle that will come through that part, and then it will pass through those two microphones that are away from the test zone. And we will measure again the sound pressure level with respect to the progression through the test zone. However, this is very easy to do in measurements and in real life where we all move ahead in time. But simulation tends to be more efficient when we work in the frequency domain directly. And this having a moving car in the frequency domain does not tend to be very efficient for simulation. So what do we do instead? Instead of having the vehicle moving, we kind of treat the thing that the microphones will be at the end moving. So we're trying to replicate an indoor pass by noise measurement procedure. So instead of doing an outdoor procedure, we have to replicate an indoor procedure where the vehicle is fixed in an anechoic room, and then we have microphones all around it. And with some clever post-processing, taking into account the phase shift of the microphones, we can have our pass by noise um, curve, and it's the same as the one that we got from the previous measurement technique. So this is a way of doing that. However, this brings an additional problem of post-processing, which is how we have a number of microphones that we have to post-process. This can become quite tricky to do if you're not familiar with how this works. The second part was about tackling larger problems, and these what do we mean by larger problems? Well, in most cases, larger problems means probably a larger a larger model in the sense of a larger item, a larger vehicle. Instead of going through pass by noise simulation for a car, we go through it for a vehicle, so for a truck, which is again needs to pass specific regulation to be certified. Or it can be that we want to go higher in frequency. Very often, pass by noise is treated from 2000 to 4000 hertz, but very often OEMs want to go also higher with 5000 hertz or more. And this can become very tricky because we have a large model, we have to fill a large volume with finite elements at least, and, uh, and thus computational time can become prohibitive as well as the resources that we need to run this type of simulation. An alternative is to use a different type of solver, and this comes in the form of the DGM method. So in Actron, we have the DGM solver, which comes from the discontinuous Galerkin method. So this solver solves the linearized Euler equations as opposed to the Helmholtz equation for the frequency domain classic solver. It can be efficiently parallelized in many core architectures, and it also features GPU acceleration. So you can have results very, very fast thanks to very good optimization of the solver in parallelism. And it can also tackle large models in high frequencies because of the nature of the high order method of discontinuous Galerkin approach and the equations that we solve for that. To give you an example of what can be done with this method, here is a pressure map in decibels at 5000 hertz of a full truck. And this was solved in just 2.5 hours on two NVIDIA Tesla K80, which is a slightly older graphics card from NVIDIA. With newer cards, this will be even faster. So this can be very easily done if you want to go away from a classic card. If you go to higher frequencies, then it's easy to use this type of method to get some results also for pass by noise in a very good time frame as well. Finally, discussed before about this number of microphones that we now have to post-process. And if you have to do this manually or with a script, this can become easily confusing and it's not at all in reality user-friendly. It's not easy to do that. You don't want to focus on doing the post-processing. You want to focus on seeing the results and changing things to make the vehicle comply with pass by noise. So in Actron, we also have an automatic pass by noise post-processing output request, which is based on the IEC 61672-1 norm. And this allows us to get a fast assessment of pass by noise performance by doing this post-processing automatically and just getting the results at the end of the simulation. So far we have discussed about some of about pass-by noise regulation. How do we measure that? Why should we use simulation for this type of process? What are the challenges for simulation and what are some possible solutions? So let's now talk about what are the essential components and how we can actually perform this type of simulation. So to start, of course, we need to have an idea of our noise sources. We need to have sources that come, we can use sources that come from measurements, 1D simulation or 3D simulation. And we can also use sources from different components that can be evaluated in one simulation thanks to a specific process that's available in Action. Then we need to have our acoustic transfer functions, which can be automatically computed in Action using the car geometry model, monopole location, these are the source locations, and the pass by noise output request. Also, we can use acoustic treatments directly in this model to assess their efficiency. We can do that with and without to also check what is the difference between uh, the treatments. So right now we have our two basic components. We have the noise sources. Remember that we need to multiply the noise sources or combine the noise sources with the transfer functions. So right now we just need a way, again as I said before, to get the absolute noise level. And this is the recombination of the source definition and the acoustic transfer functions as a function of the vehicle driving conditions, the possibility to compare impact of the driving conditions on the final pass by noise level, as well as to isolate potential issues and define acoustic countermeasure strategies. So at the end, we have all of these essential components. We can start doing our simulation. So let's go through each of those specifically to see their nuances and their points. Let's start from the noise source. And for the noise source, we normally have noise sources in two different ways. We have them either in the frequency domain or in the time domain. In the frequency domain, most often they come from an engine simulation at a specific RPM. And at the end, we can have this type of waterfall plot where we can see what is the noise for between frequency and time for, uh, for our engine. We can also have a tire noise spectrum, or we can have in reality any other type of excitation in the frequency domain. It just has to be a signal in the frequency domain, and we can use that as a noise source very easily. The second type would be in the time domain, meaning that we have a time signal. And most often this comes either from a 1D CFD simulation for exhaust noise, or it can come from measurement data. And there are also some other things that we can use as well, but it doesn't really matter where it comes from. It just matters that it is acoustic pressure versus time, and this can be very readily used in our simulation. So these are the noise sources that we can use directly in our in our simulation. Now about the acoustic transfer functions, as the words say, this is a transfer function, meaning that we try to put a unitary excitation to see how the noise goes from this source up to a measuring point, which is normally a microphone. And most often that means that we use unit sources or it has an amplitude of 1. And in lots of cases, we use monopoles as the first approximation. It does not mean that we have to use only monopoles, of course. We can use any other type of noise source. But monopoles are as the first approximations. If we have to do that for tire noise, we can use a more expensive simulation of tire noise that comes from a nonlinear solver and so on. For the exhaust, it is similar. We can also take into account the 3D simulation of the complete exhaust system to use as a noise source in the pass by noise simulation. All of these noise sources can be used in one calculation using the multiple load case capability in Actron. And of course, we need to have a way to automatically create the exterior acoustic mesh. And this is because this will allow us to be much faster, as I will show in a bit, as well as make it easier for the people to use this tool. And this exterior acoustic mesh that's created automatically can be adapted to the frequency to solve. At the end, if we set this model with our noise sources, our mesh, and everything, then we just need to create an automatic dedicated post-processing output request for pass-by noise that allows us to get directly the acoustic transfer functions for this simulation, where we just need to provide some information such as the car length, direction, the speed, the microphone position, and so on. So we just need to give in reality what will be the actual test zone. I would like to focus just a bit more on the adaptive meshing and high-performance computing point of view of pass-by noise simulations, and this is mostly because they tend to be very expensive overall, as I will also show you in a few of the case studies later on. But it's very important that we can actually solve those, not in a week or more time, but instead we can have that during the day so we can do many more iterations of our configuration. And the first one was the adaptive mesh that I briefly touched upon before. And adaptive mesh means that in specific frequencies, we use a specific mesh. The reason for that is that if we want to have only one mesh, then this mesh needs to support the highest frequency. And that means that for the lower frequencies, where the wavelength is much larger, this tends to be overkill. So what we do instead is that we have in the solver an automatic way of generating different meshes for different frequency ranges. And this mesh is adapted exactly to a specific frequency range, thus making the calculation uh, much more, uh, much cheaper in the lower frequencies, and also keep the cost correct in the higher frequencies. This means optimizing the calculation for the specific frequency range. Going on then to see how this applies and how we can also add some more optimization to our solver, I'm showing here this plot where the reference model is what you see here on the left, the 2000 hertz model, but used for the complete frequency spectrum from 100 hertz, let's say, or 10 hertz or whatever, up to 2000 hertz. And this takes about 13 hours and 20 minutes to run. If we just apply the adaptive meshing procedure, then we can reduce that by 5 hours already to 8 hours. Still, here we are almost in the overnight calculation time, meaning that we put it in the afternoon, come back in the morning, and we see that. So that's an improvement, but maybe not the improvement that we want in reality. So if we then try to apply further optimization to the solver, then we can have this adaptive meshing plus solver optimization bar here, which is about 5 hours and a few minutes. And this is really starting to become interesting because 5 hours means that we can start the simulation in the morning, and we have the results in the afternoon, put another simulation overnight, and continue on this process so it becomes much more efficient. If we then add to that 8 CPUs, just 8 CPUs, then we can have our simulation reduced from 13 hours and 20 minutes to about 1 hour and 10 minutes for an 11 times the speed up. This is for a pass-by noise analysis up to 2000 hertz. So we can have actually not just one simulation of pass-by noise during the day, but we can just do modifications, change things, add things, and then run it again and do the same again and again and again, at least a few times per day. So you can see that this can help increase the productivity for pass-by noise simulation. Finally, the last part of these simulations is, of course, post-processing. And post-processing is not just in the form of, okay, here are my acoustic transfer functions. That is good. Here's my pass by noise level. Again, that gives me an idea. But again, we need to have also a further idea about how we can improve these results with respect to the maximum allowed levels. So simulation can provide you with pressure maps such as the one that you see here in the top right-hand corner to tell us how noise propagates around the vehicle. It can give us an idea of the contribution of the different excitation through this type of contribution plot. So we can see in the whole frequency spectrum or in specific frequencies which noise source contributes more to the total noise. And then we can go ahead and do some modifications to that specific noise source. It can actually provide us with the absorption in its acoustic treatment that we add as a countermeasure. And also at the end, we can listen to the noise that the vehicle will make. So we have this realization technique that allows us to get the signal, convert it to an audio file, and listen to the noise that it makes. And you may think, okay, that sounds a bit weird, but of course, very often you want to do pass-by noise simulations, meaning that you want to reduce the pass-by noise level, but at the same time keep a specific signature sound that the vehicle makes. So it is very, very important for quite a lot of brands to have this type of possibility to listen to the noise. Also, this can be a great communication level with upper management, where if you show them a curve, they will not really understand it. But if you make them listen to the noise, then they will definitely say, okay, this is good, this is not good. You saw it in the previous slides about how to do these simulations. I did not talk about the source recombination. And this is because I want to spend a specific amount of time talking about the workflow manager, because this tool can allow us to have a much easier way of recombining the sources and seeing what could happen for different types of sources and acoustic transfer functions. So let's take a look at this. And what is the workflow manager and how does it work? So I talked about it a bit before, but what it is in reality is just a container of vertical solutions where we define the workflow that users will follow, the expected input data, the possible combinations, and at the end, what are the outputs. And currently, in the current version of Action, we have two types of verticals available. One is for pass-by noise, which is the topic of today's webinar, and the second is for electric motor noise, which also can be interesting for automotive OEMs. And let's see how the pass-by noise vertical works. So in reality, the workflow of the pass-by noise vertical is split into five different sections, where this represents a storyboard, meaning that you go from one to the end. So as the first step, we provide the source strengths, and the second step, we provide the transfer functions. We provide the information on the vehicle and the track, and at the end, we do our analysis in the last tab. So we have a tab-based approach where you go from the first tab to the last tab to get your results. And let's see each one of those specifically. In the first tab, we can provide the source strengths, and this can be again in the form of uh, tire noise, exhaust noise. It doesn't really matter. What matters is that it is either in the frequency domain or in the time domain. You can also provide the dependency with RPM or with speed. So we have lots of different options here for how we can provide the noise sources. After we have done that, we can go ahead and provide the transfer function information. This can come from Action by importing a PLT file that contains the transfer functions. And we can also define what this transfer function is in terms of pressure to pressure, pressure to mass flow rate, and so on. So we have a different number of combinations that are possible for the different transfer functions. Once we have done that, we can go ahead and provide the information on the track, such as the speed of the vehicle, the track length, and the vehicle length. We define the track conditions. We define a number of vehicles, and this is why do we do this? This is because we can have various different combinations of sources, and we can try to see again these what if scenarios. So what if we do this? What if my vehicle looks like this? What if my vehicle behaves like that? So we can define different vehicle configurations by setting track conditions and source and transfer functions. So here we select really how we combine our sources, transfer functions, and test conditions. And at the end, we go ahead and perform the analysis. So here we can select the different vehicles to analyze. We can get a contribution plot at the one that you see at the top, where you can show the total contribution of the noise as well as the specific source contributions. We can assess the global performance for pass-by noise, and also we can define our targets for that. So this is how this works in terms of the source recombination. You can see that this is a very powerful tool that can be used also by non-experts of simulation, which can be a very important asset when creating pass-by noise simulations. So what are some of our successes? So I have talked a lot about what we can do and how we can do things, but how have we applied that already in the field? And here we'll talk about a few case studies, some longer, some shorter, to showcase how we have done pass-by noise with Action in the past. And the first test case comes from Renault, and this is the numerical assessment of a car pass-by noise. It was presented in our conference in 2016. So here, what they wanted to know at Renault is how the transfer functions behave. So they wanted to evaluate the acoustic transfer functions for a quite large vehicle. We have a number of different sources, as you can see here, and you have a specific test zone that you can see at the top of the slide. The important thing about this test case is that transfer functions are computed for this car up to 5,000 hertz. So this is a quite high frequency simulation. So to cope with that, they created three different models, one for the low frequency, one for the medium frequency range, and one for the high frequency. And the reason for that is that you can see that in the plot at the top right, where you can see that the cost starts increasing as we go up in frequency, and we start to become too high, and we start to modify, we start to switch to a different model, and again until it starts increasing again and again and again. But if you imagine that we just were using the last model up to 5,000 hertz, then we'll just have the cost being always like this for each frequency. So it will be very, very expensive. So for them, it was important to assess the geometry and or acoustic treatment modification influence on the acoustic transfer functions, but to do that at the low computational time. And this was enabled largely by mesh adaptivity at this point of view. So some of the key features, according to Renault, were the adaptive exterior acoustic component, meaning that we can modify our exterior mesh with frequency. The multiple load case computation capability, meaning we can put various different noise sources together and evaluate them independently. And also the post-processing capabilities of Action at that point. Let's now take a look at the second case study, which is about how Autonium and Jaguar Land Rover consider the design complexity of engine encapsulation. And for those that are not familiar with this term, engine encapsulation is when we apply a number of covers on an engine to essentially dissipate noise. So here they use engine-mounted and body-mounted encapsulation. And to do this type of test and measurement to do this type of evaluation, we need to use a vibroacoustic simulation to accurately predict the performance of the encapsulation, which could include both solid materials, such as aluminum and so on, as well as for elastic materials and trims. So for this case, the simulation setup was the wrap mesh of the vehicle, just a unit velocity excitation on the engine surface to just calculate the acoustic transfer function. A 3D representation of the acoustic treatments and the exterior acoustic mesh was created with an adaptive, perfectly matched layer. And here they considered the simulation from 400 hertz to 2 kilohertz with a 15 hertz step. And the total computation time was 12 hours. So this is still in the overnight range of time. Here they have used a large amount of acoustic treatments, as you can see, not just around the engine, but also in the floor and, of course, just in the engine bay. To see some results here, they did some correlation with measurements. What you can see here on the left-hand side is the top side, where we compare with at the top narrowband and the bottom third octave band simulations and measurements. And you can see that the correlation is quite good between those, as well as for the bottom side of things, where we can get a very good correlation between simulations and measurements. What I want to showcase with those two cases is that we can have very fast results in a very efficient manner, but at the same time, they're very, very accurate. It can help us, can give us confidence to the model that we can do our modifications and what if scenarios. Some final case studies. These are just going from a smaller vehicle to a larger vehicle, as you will see. So I will start with the pathfinders for motorbikes. This is the case for Royal Enfield, motorbike constructor. So what they wanted to do was they wanted to come into the European market, so they have to maintain you have to respect the pass by noise regulation in Europe, while still maintaining the specific signature rumble that the Royal Enfield motorcycle does. So what they did is they used a simulation that combined Adams, Carr, MSC Nastran, and Atran to help predict noise levels from the three dominant noise sources, the air intake, the engine, and the exhaust line. And at the end, when they did that, they found that they had better predictability to their new vehicle launch cycles, meaning that they can have a more consistent way of evaluating pass-by noise. They could identify major noise sources, and they can also save in cost and time in the entire design to launch process, where they have very accurate results. Going into a vehicle, and this is the case of Subaru, this is the more advanced case of pass-by noise where we combine pretty much everything. Not just what happens in the exterior of the car, but also what happens in the interior of the car, which sometimes they can have an effect since we can have some damping there that can actually change how pass-by noise is emitted. So in this case, they create both an exterior acoustic model as well as a structure and interior acoustic model. They identified the noise sources by measurement, and then in a four-step process, they did the exterior propagation, the body transmission, and the interior propagation at the end to have the interior noise and the exterior noise simulation. So at the end, as you can see at the bottom plots, and maybe they're not particularly visible, but what you can see is that they have very good correlation to interior noise levels, pass-by noise levels, as well as um, floor transmission loss. So at the end, they were able to have very good predictions during the development stages of the vehicle, and at the same time provide countermeasures and evaluate their performance. Going to a slightly larger vehicle, and now we go a bit into the van range. Here, this is the case of the General Motor Corporation, where what they want to do was they want to comply with regulations, and they have been using simulation for a few years now, but these computations were taking a very long time, even for 2000 hertz, which is relatively low in terms of frequency. And the goal was to go to 4000 hertz. So the simulation that they were doing before was a boundary element method simulation. And what they did is they switched to action and the finite element method, as well as the specific capabilities that we discussed before on adaptive mesh and high performance computing. And at the end, what they were able to do, they were able to reduce the calculation time by 98% from 100 plus hours to about 2 hours for up to 2000 hertz of frequency. And at the same time, achieve very good correlation between measurements and simulation, which gives them confidence in the solution. And now the next step will be to go ahead and reach this 4000 hertz um, target that they have already. So you see that HPC and adaptive mesh can become a very important tool when we want to reduce the computational time of our pass-by noise simulations, even for relatively large vehicles. And finally, let's talk about some track pass-by noise, and this was presented again in our conference by Volvo. And the idea here was to understand the engine contribution to the pass-by noise test, including the encapsulation and cooling radiator effects. So thanks to Actron's efficient multiple source handling, forest modeling, and acoustic mesh activity, they were able to do a precise reproduction of the static pass-by noise test. So at the end, they achieved very good correlation between test and actual results. This flexibility of Actron allowed them to do parametric studies on encapsulation concepts, and also the multiple noise source handling in one computation give them the possibility to rank the transfer path functions. So you can see that simulation can provide lots of benefits and lots of ways to get insight from this type of simulations. So to summarize what we have seen here, we have seen that simulation can be used very effectively instead of measurements, as it can provide accurate results, allow us to virtually test more configurations at greater granularity and with better insight, and also it can be implemented earlier in the development process. So it can be a very big asset for this type of noise, of pass-by noise. It can provide an efficient and fast approach by utilizing adaptive meshing for faster computations, by employing state-of-the-art solvers with excellent parallelism capabilities, and also providing the appropriate solver for each problem, such as when to use the classic frequency domain solver. I want to use the high order discontinuous Galois solver for larger models and higher frequencies. And finally, we can have a dedicated interface for pass-by noise, where we can perform the combination of noise sources and acoustic transfer functions to obtain the noise levels, identify problematic noise sources and paths, and also perform what-if scenarios to reduce the final pass-by noise. If you want to learn more about how we apply Actron to industrial problems, including pass-by noise, you can go ahead and read our acoustics ebook. It includes a few pass-by noise case studies as well. And if you would like to learn even more about how Actron has been used by our customers, including for pass-by noise, you can join our virtual Hexagon Live Design Engineering Conference that will be held between the 12th and 14th of October, where we feature more than 30 presentations by our customers on acoustic simulation. Besides acoustics, you also have the possibility to see other parts of the MSC software portfolio, such as structure, system dynamics, CFD, and so on. So you can go to this link, you can register. It is completely free. There is no cost. You can have more than 880 presentations over these tracks that you see over here. So with that, I would like to open the floor to a Q&A. So please ask your questions at the Q&A chat box, and I will reply to that just in a moment. If you have any larger questions or any further questions, feel free to contact me at this specific address. I'll be very happy to come back to you with answers to your questions. So thank you again, and let's go to the Q&A session.